We will go ahead and I will pass the mic to Michael Levy from Baringa, who's going to talk about the Gracie program and the reports. Thank you, Michael. I'll let you go ahead and share your screen and take it away.
Excellent. Thanks, John. Just quick introduction on my end. Michael Levy, I'm based out of Atlanta, in Georgia. Been doing utility strategy consulting for about 16 years and work at a management consulting firm called Baringa. We are about 2,000 people globally and are cross industry, but our deepest industry spike is within energy. And I'm a partner and run the utilities practice for the US. So most of my clients are utilities like some of the folks on this call, and we also do a lot of work with the Department of Energy. And while our work is across many parts of the different functions within the utility, a lot of the things that we do center around asset resilience, and notably forecasting resilience risk at the asset level in dollars so that you can determine how to best invest against those. The DOE hired us to support 11 Western state energy offices in this Gracie program that he had mentioned. And that was a year-long program that actually wrapped up about a month and a half ago. And part of our work was two core deliverables, both of which you should have access to soon. One of them is already published on the Colorado State Energy Office webpage under the 401 defunding. And then the second actually will be part of a Baringa landing page that will have links to all the different state for the grid reports and grid resilience reports, as well as links to two different webinars that we hosted throughout. So I've got a preview of what some of that content across the two deliverables looks like today, but maybe as I'm pulling that up, would welcome any questions before I jump in. Great. You guys wouldn't mind just confirming if you can see my screen?
Yep, we can see it. It looks great.
Excellent. So we covered this already, the 11 Western states. And the intent of the project really was to provide content for the state energy offices as well as the utilities that were applying for the GRIP funding on what is the outlook of extreme weather risk in your state, and how is that coincident with different types of power assets, and what does that mean for the future in the way you should be thinking about prioritizing different types of investments and adaptation strategies for given those two things. So we've got two deliverables. The first that I'm going to give you a preview on is called the Grid Resilience Report. And effectively what we've done is overlaid downscale climate projections at the county level. And we looked at wind, flood, heat, cold, wildfire, and drought. And that overlay was done on different types of utility assets. So we've got one view that shows the coincidence of extreme weather projections and distribution assets. And in that case, since we didn't have the details on where all of the distribution assets are, because the entire analysis was done based on publicly available data, we used population weights in each of the counties as a way to weight the density and the type of exposure. And you'll see some examples of that momentarily. For transmission and distribution, transmission substations, the lines themselves, and also the plants, that data is publicly available. And so what you'll see on those views is an overlay of the climate projections and those types of assets. So you have a D view, a bulk power system view, and then we've got some statistical graphs that may show things related to how those extreme weather risks are changing over time, and seasonality and various insights like that. So this is an example of the fire weather index, which is a publicly available index from Argonne National Labs climber tool. And we've overlaid that, excuse me, we've overlaid that and done a population weighting. So the way that you can interpret this chart is the color indicates the severity of the hazard, and the size of the bubble is based on the population weighting. So a darker, larger bubble would be more risk. And you can see that on the left-hand side, we've got the historic fire weather index, and then the right-hand side is showing end of century. And Mesa County is probably a notable area where that bubble is 8% darker, meaning there's an 8% greater risk of exposure from wildfires. Um, the other counties, the risk of wildfire is not changing as materially, but again, you can see kind of where the population and subsequently the distribution, the density of distribution assets are concentrated, and then how that overlays with fire. Here's another view of distribution assets and wind. We looked at historic wind data and then empirically derived different return periods. So in this case, the return period we're looking at is the 100-year wind speed. So basically what that means is every 100 years, we're expecting on average to see these wind speeds or greater. And if you look at Larimer County, the 100-year return period, so like that would be like a 1% annual probability. Larimer County, that means that there's a 1% chance in any given year of seeing 130 miles per hour wind speed or more. That is really fast wind speed. Um, and even 81 miles an hour, which you can see, I don't know which county that is, but that's, pretty up there. And generally, you're going to see pretty severe damage to your assets as wind is approaching anywhere near there. And so one way to be thinking about this type of analysis is in the way that you're selecting your design standards. Just for some quick probability math, if I've got an asset that is lasting 50 years and the chance of having a design standard exceeding event is 1%, then that means over that 50-year period, there is a 35% chance that I see an event like that at least once. Um, if you get to a 1 in 50-year return period, which might actually be the case for the design standard exceeding event here, that 35% grows to 64%. So that means that over the useful life of the asset, assuming your poles last 50 years, there's a 2/3 chance that it's going to fail before the end of its useful life. It's these kinds of statistics that kind of really bring into perspective how important it is to be thinking about designing your assets based on what the extreme weather, the tail risk is, because the assets' useful lives are so long. And then, of course, there's lots of other things that play into outages as it relates to extreme wind, vegetation density, the age and condition of the assets. But this is really just looking at coincidence of wind speed and distribution assets. Any questions on this one?
Um, Michael, I would I would just mention that we I really appreciated this finding in particular. Especially all those high winds along the Continental Divide and the Front Range. I know that all of our utility partners are thinking about wind frequently, but I think a lot of folks in the greater public don't think about wind so much in terms of the impacts to the utility system.
Yeah, for sure. So here's another view of another hazard, but now we're looking at different types of assets. So the lines are transmission lines, high voltage transmission lines, and then the bubbles indicate different generating assets, and then the size of the bubble is the nameplate capacity. So what you're looking for on this map really would be a coincidence of thermal assets with high temperature increases because thermal assets, they derate when it gets super hot. And the other thing that happens when it gets super hot is people use more power. So if supply is derating and demand is going up, that can cause problems. And so this view is showing a mid-century view. So by 2050 for RCP 8.5, which is a extreme climate scenario. And you can see in the middle of the state here, there's a lot of thermal assets that would be exposed to these extreme heat, where the average maximum temperature is growing pretty substantially over time. And the charts that I'm showing, I realize I kind of jumped around different hazards, different assets, but the full pack has every combination thereof. So each hazard, you get a D view, you get a G and T view, and then you get the statistical view. Other questions on the grid resilience report before I jump into the state of the grid report? Great. So while the grid resilience report was more based on forward-looking climate projections, the state of the grid report was really looking at historic weather data, and then more importantly, the coincidence, both spatially and temporally, of historic weather data and outages. And so one of the things that we looked at was what is the coincidence of 90th percentile weather with extreme outages? In this chart on the right, the x-axis is the absolute outage severity. So this is over a 4-year period from 18 to 22, excuse me, 5-year period. What is the total number of custom interruptions that each type of extreme hazard causes? And then the relative outage severity is basically looking at the number or the average percentage of that county that experiences the average percentage of that excuse me, the median percentage of that county that experiences an interruption. So 50% in this case would mean that when that event hits particular counties, that on average, 50% of the customers experience an outage. So the higher that would be an indication of severity versus the x-axis is more of an indication of frequency. And I guess another way to think about the y-axis is how spatially distributed is the event. So if I've got an event like a windstorm that sweeps across the state, then it's going to affect more customers. And also, when it does affect the customers, more of that county will be affected. And so you can see here what types of events tend to be most extreme. And then one other thing that I'll draw is this is denominated exclusively in outages, not economic impact. So wildfire obviously is in this, compared to windstorms, is not causing as much damage on a relative basis for, excuse me, as much outages. It's not commenting on the fact that fires are absolutely devastating and can cause severe economic damage. So hopefully that's clear. But I think this is like a really interesting look because it shows you if I'm trying to rank the hazards that I want to be most concerned with, these ones in pink, they're the ones that are really giving me a lot of problems with reliability because they tend to be both severe, in aggregate, and also affect large portions of the state when they do hit. And you've got some statistics here on like the count of events, the median outage ratio. Again, that's the percentage of the median percentage of the county that has an outage. So if I have 100 customers and 50 are out, that'd be 50% of the customers in the county. And then the total interruptions and the average customers per event. Yep. And this was leveraging Eagle Eye data for outage data. Yep. Questions here? This is a similar view, but just ranking the hazards based on their severity and their contribution to the total. And you can see, again, these three, windstorm, extreme cold, and winter storm, just like you saw on this slide, these are really, as it relates to outages, not necessarily damage, which is why we left wildfire off here. These are the ones that you really need to be worrying about the most. And subsequently, those would be the ones that the hazards where you should be focusing the most on the types of adaptations that address those hazards. I think the good news is, as it relates to winter storms and windstorms, the types of adaptations that you make. When I say adaptations, I mean investments. So that's undergrounding, upgrading pole class, tree trimming, all the things that you're doing. Um, those are going to be really effective ways at addressing these types of risks. Hazards, excuse me. Yep. And then kind of just segueing to types of adaptations, cost versus the types of hazards they address. This is just a high level mapping. It's non-exhaustive, but it's showing you what type of asset by asset class, what are the types of things that you could do, and then which hazards they address. So when you're looking to submit for your grant, or if you're looking to decide how should I be thinking about prioritizing resilience investments integrated into the investment planning that I'm doing, given what you're exposed to and the things that are causing the most outages, those should be the things that you're prioritizing. And then I guess I think this is my last slide. Yeah, I've got two more. There's different kind of levels of maturity in terms of what you do with all of this data, right? And what we've just shown you kind of would be in this category here, this more strategic analysis where the spatial resolution is very coarse. It's at the county level. We're using publicly available data, and we're just commenting on the trends, but we're not actually like quantifying risk per se. Whereas if you were doing a vulnerability study, a vulnerability assessment, then you'd be looking to use downscale climate projections, and the output would either be a risk score or quantified dollars of risk. So this is something that we help utilities around the US do, is forecast asset level dollars of risk from extreme weather. And then once you know what that risk is and where it is and when, then you can actually calculate the NPV of different investment actions against those. So like maybe like a very basic example of that would be if I've got a utility pole and it's rated at 70 miles per hour wind speed, I can use downscale climate projections to estimate the likelihood that that wind speed is exceeded. That gives me a probability of failure. I can forecast that because I have the climate projections for that exceedance threshold. And then I multiply by the cost of failure, which would include both the cost to the utility to repair the asset reactively, as well as the cost of the value of lost load, economic value of lost load to the customers, so downtime cost. That gives me expected cost, that's forecast out. And then if I make an investment, that reduces the failure likelihood. So let's say I underground the asset, that would reduce the probability of failure from wind to zero, because now the assets, and then I can take a benefit and discount that against the investment. Similarly, I could upgrade the class of the pole, and that would lower my probability of failure because it's less sensitive to extreme wind. And then that would also give me a benefit that I could discount against my costs. So very basic example there, but hopefully you guys were tracking with that. Great. I think that's it, John, on my end.
Michael, I had a question for you. A lot of this is focused on the impact of wind, and I'm just curious. We know that as the climate changes, we're experiencing and expecting more heat, extreme heat, and
Sure.
drought, floods. But what about the impact on wind?
How is that expected to change over time?
Yes.
Yeah, it's a great question. Outside of hurricane prone areas in the US, wind actually doesn't have a super strong climate signal, meaning that there's not a strong attribution of climate, like a change in climate to how wind is going to change. And if anything, actually, the expectation is that like wind is basically moving from high pressure to low pressure. And as the temperature gradients between those gets closer because of warming, then it's expected there's going to actually be like less wind generally. But I think what we will see is that the cumulative amount of wind may end up being less, but the tail risk of wind may be unchanged or actually even more severe. And that's coming from things like derechos and polar vortexes. But the climate science has not yet kind of established a strong attribution between, increased emissions intensity in the atmosphere and any change in frequency or severity of those types of events. Long answer, but hopefully it addressed your question.
Yeah, it did. I
Go
see
ahead,
we have a
Rick.
question from Rick Ragel from ARPA.
Yeah, Michael, John, thank you. Well, I had a question. You mentioned that a lot of the data from the especially with the wind impact and some of the outages it causes comes from publicly available information. But I
That's
wonder
right.
how many of our small municipal utilities actually publicize or or report those kinds of issues. I just wonder if they don't, how can they demonstrate the need from the impact from the wind and the cold weather?
Yeah, it's a great question. I can't remember. I think it was NOAA data. It was either NOAA data or WRCC that we used, and we derived based on that data the return periods for. So that was a historic return interval. So when we say this is 81 miles per hour for the 100-year return period, we there are commercially available downscale climate projections for wind. It's just for this particular project, we only used public data. And since in the West, for the reasons I mentioned, the expectation was that historic data was sufficient for predicting future risk because you're not hurricane prone. But the way that you're establishing that risk and the exposure is generally going to be through either empirically derived fragility curves or physics-based models. And so effectively what you do is you may not have data historically that correlates asset failures and vegetation density and extreme wind speed, in which case you wouldn't be able to empirically derive it. So you can use a physics-based model that says, well, we know that this asset is designed to withstand this type of a wind speed. This is the chance that that wind speed is exceeded in this area, and therefore that's the probability of failure.
Okay, so they could take that information from publicly available information and just work it into their own model.
Yeah, and it's useful for two reasons. One is it's allowing you to say, well, how much risk do we have in our system? And then also, I guess three reasons. How much risk do we have in our system? Where is the risk? And when we do replace these assets, should we replace them again like for like, or should we consider, what the marginal cost of upgrading the pole class is? A really basic example of this would be even if you assume that the weather is not changing over time. Let's assume that the weather is static. So the chance of having a design certainty exceeding event over the next 100 years is the same. It's unchanged. But I now have added 10 hospitals on this feeder, right? That would be a really good reason to say, well, even though the exposure is not changing, the risk is because the cost of failure, the expected cost of failure is higher, and therefore maybe it does make sense to upgrade to a stronger class pole. So you want to look at both the failure likelihood as well as the cost of failure, which is gives you your expected cost. So then that's the basis for your NPV calculation.
Okay, thank you.
I see a question from Julie, expressing concern, hope this kind of data will be continue to be collected. Yeah, I agree, Julie. And I do think that there's like a concerted effort on folks to be downloading these data sources and archiving them to make sure that they are always publicly available. Baringa, so the first version of this report, the grid resilience report, that is already on the Colorado website. The second one, the state of the grid report, which is more the historic looking correlation of outages and extreme weather, like actuals, that will be on a Baringa landing page, which should be published this month. But that's going to have a link to all the reports and the webinars across all states. So once that's live, then we'll make sure that you guys have a copy of that. But in the meantime, you've got the full grid resilience report across all hazards.
And Michael, I just well, I hijacked what you were sharing there, and I put on this screen just to help respond a little bit to Rick's question about the data set that you have from Eagle Eye, and I think this kind of indicates that Eagle Eye is it's maybe you can talk a little bit more about that and
Sure.
what some of the gaps in that data is.
Yeah, so historic outage data is obviously very useful when you're doing this type of analysis, but it's not always a requirement. If I like the most basic version of an analysis would just be a simple threshold-based analysis where you say, if the weather exceeds this value, then failure occurs. So a very simple example of that would be if I have a substation, I know it's elevated at 3 feet. I can look at what is the chances that there'll be 3 feet or more flooding at that location. I don't need historic weather data, historic flooding information. I don't need any of that to be able to say that 3 feet is where it's going to be problematic. Now, in the case of wind, if you're wanting to derive a fragility curve where the from the historic outage data, and you're wanting to like test different features like how does pole class or material or vegetation density, like how does that affect the sensitivity to wind? When you're creating a regression, you need training data. But so obviously historic outage data is very useful in that context, but it's not a requirement. You can still do a lot with very basic information like design standards alone. And our recommendation is start with what you have, and start incorporating extreme weather risk into the way that you're doing asset planning now, and then start thinking about, well, how can we make our models more sophisticated later on?
Great, thank you
Any
very
other
much.
questions? Yeah, and I'll put my email here in the chat. So if you guys have any other follow-ups or want to reach out directly, then certainly feel free.
Excellent. Yeah, and we hope to get that report updated to our website soon, next few weeks or so. And if not, Michael mentioned that there will be that landing page from Baringa. Will that be on Baringa's website or the DOE's website?
Yeah, it'll be on Baringa's website, and then it says sponsored by DOE, and there's a bunch of disclaimer language on there saying they sponsored the work. Yeah.
Excellent.